Hello, welcome to an Ozen engineering video where we talk about simulation with Ansys products and show you how to build different types of models, how to execute them, give tips and tricks using these tools. In this particular video, I'd like to touch upon Ansys Icepak. Particularly, I'm going to concentrate on something called zoom-in modeling. In other words, this is more of doing a sub-model inside an existing system or inside an existing Icepak model, where what we want to do is resolve more details in only a small section of this existing model and capture the details within this volume. For example, this would come in very handy if you have multiple repeating, geometry, like parallel PCB boards that are fairly similar to each other, but there's a large number of them within the whole system. So the whole system may have all these PCBs with little detail, but then one can resolve only one of the PCBs in detail using this zoom-in modeling approach. So, I'm going to go ahead and present an example, and it's going to make more sense. So I have our workbench model open, and what I want to do is go to Component Systems and drop an Icepak object. And then what we want to do is import an existing Icepak model. So I go do a right click on Setup and want to import a TZR file. So I'm going to hit Browse. I'm going to go to the relevant folder and hit Open. So Icepak quickly opens up the file. I'm going to click isometric view to give you a better view of our domain. So we have these 6 fans that are cooling these electronics components, and as you can see, it's a pretty repetitive structure inside the system. So each of these yellow plates represent a PCB, and they each have 30 watts of total power on those. I'm going to go back to my workbench window, and I'm going to save this model with a new name onto the folder that I work on. So let's just call it Rack New. So if we go back to our Icepak model, we want to start doing meshing. We're going to go click the Generate Mesh button, Mesh Control button. And we want to set the maximum sizes at 3 centimeters. So once we did the global mesh size, let's do some local meshing sizes. Let's select some objects. I'm going to go ahead, pick opening 1, use per object parameters, and I want to have Y cell, 10 cells in the Y direction. Let's do the same for opening 2. Then we have a lot of plate objects, so by using the Shift button, I can select all the plates, and again mark this, and I want to define a low end height and a high end height for ourselves. All right, and then let's go select block number 3 and do a Y count of 4, and then let's hit done. And then to generate the mesh, we simply hit the generate button, and at the top right corner you can see the progress as the mesher is working, and it quickly generated around 125,000 elements, and we'd like to display it. So next step is to display. Let's make a cut plane, and we can see the mesh generated, and it does look to be good for the purposes of this analysis. Another thing is we want to check the quality. Face alignment, you want to be over 5%. Skewness, you want to be over 2%, and this looks like a quality mesh. That should get us a decent solution. So let's start setting up our model. Let's go to our solution settings. We're gonna click basic settings, where we're gonna set 300 iterations, and let's keep the energy the same. Hit accept. Let's go to advanced settings, and then let's set pressure and momentum. Defaults look good, so we can hit accept. Let's go to then the problem setup with basic parameters. Here we want to solve for both flow and temperature. We're not gonna do any radiation. And then we're going to keep the turbulence model. We'll stick with 0 equation. And then let's hit accept. We also want to add some monitor points at some plates. So let's pick plate 2.1 and then drag it and drop it under points. So this is going to be a monitor point, and if we don't change anything, it's gonna show us temperature at every iteration. So let's also do this for plate 2.2. Before we execute the run, it's always a good idea to save. So let's hit save project, and we can see that the project is done saving here at the console. And then we're gonna go do the run. We go to the top ribbon, click on the calculator, and then we're also gonna do a sequential solution of flow and energy equation. This is going to speed up the solution process. And this is typically suggested if you don't have a natural convection type model, or flow with physics of buoyancy, where that is critical. And then now we can click the start solution button. This is going to start writing an input file for the Fluent solver. Right now the model's being translated into Fluent. Very soon an execution in Fluent will start, and then we can track the residuals and monitor point values, in this case the temperature at plates 2.1 and 2.2 as the solution progresses. So this is the window we get once we have a solution. And what we do see is we did a sequential solution where the first 100 maybe 10, 20 iterations, you can see it not solve the energy equation. It converged the flow equation to 3 orders of magnitude, and therefore the monitor also, the temperatures that were monitored stayed at 20 degrees C. But then, we turned on the energy, and then with just a couple of iterations, that did converge to a higher value, as you can see through the monitor. So let's hit done. And then now we want to look into the results. So now we have the solution. Let's do some post-processing. Typically we want to see temperatures, velocity field on different locations. And we can go about posting a couple of different ways. We can click the post here, use these functions. Another quick way to do is use these 2 buttons, which I frequently do. So I'm going to go ahead, do object face. So what this will do is it will let us pick any of these objects and then show the temperatures on different sides of that particular object. So I'm going to go ahead, just pick our plate 2.2, hit accept. I want all temperatures shown on all faces. So for that purpose, I'm going to hit show contours, select parameters. Default is temperature, which I'm going to stay in. I'm going to put the min-max temperature limits not to global, but for this object, and hit apply. So this is quickly going to give us the temperature field on the faces of our PCB. Once I'm satisfied with the result, if I want to turn it off, I can inactivate it, or if I want to recover, I can go under inactive and activate it to see it again. So this is our object face. I'm going to hide it. I'm going to say done. And then I'm going to maybe go do a plane cut. This is also very useful. This plane, which we define, can be at a constant x, y, or z direction, or you can define to a point and normal, etc. And it's going to cut through all of the objects. So if we do y plane through center, so somewhere roughly here, for example, we can look at the mesh. Well, maybe not. Let's do show contours. Oh, we did not do create. So let's do show contours. Click parameters. This time I want to look at flow speed. And then let's stick to global limits. Let's hit apply. And this will be our velocity field. So here, the color scale, because it's global limits, it's a bit on the lower side. So maybe what I want to do is switch to this object and then, get more details on the flow speed. So each of these fans are pushing flow across to cool our plates, which are generating heat. So we can see the speed along this cut. Or, again, we can go take a look back at temperature, hit apply. So we can see obviously that the boards are hotter. It's dissipating heat into the air, where air is kind of cooler away from the plates, which all makes sense. So that's good. So then, once we're comfortable, we can hit done, and then same way, we can hide this view. Another way of post-processing that I like is, again, by using object face, but do particle traces. So let's go ahead, pick the fans. So I'm gonna hold my finger on the control button so I can select all 6 fans and hit accept. And I say show particle traces and hit parameters. And we can color, it's gonna send some, show particle traces. We can color those, for example, by temperature. And let's, make some changes here to get, meaningful results. Okay, it's 24. Let's make that maybe wider. And let's hit apply. So what we do see is the streamlines that come out of the fans, and then they're colored by temperature. And maybe we define these kind of cones. What if we made them larger? So maybe I think I like this better. The arrows look a bit better at a higher size. And you know, we can also show the speed where you know, we see what's happening. So the flow is getting turned due to the geometry near the exit. And then we can do animate, and we can see, you know, how the flow behaves. So once we're satisfied with the post-processing, we were now gonna go working on our zoom in or sub model. So we go to post, and then here we want to create a zoom in model. And once we click on it, it's going to bring up our zoom in zone. So using a rectangular box, you know, define min, max, x, y, z's, we're going to define our zoom in zone or our submodel. So let's start putting in some numbers here to define our box. And we're going to isolate our the second PCB. So let's make sure, you know, this makes sense. Okay, see, as you can see, it kind of covers nicely around the second or the third board. And I'm gonna go ahead, hit accept. So what we see is this objects overlapping, and then we need to resize so that, you know, we don't run into this issue. So we click the button, and then that's done. Next step is going back to our Icepak model. And then drop a new Icepak object. Let's name it zoom in. Then let's take a results block, drop it into solution, which is going to essentially link the solution from our zoom in model to the results block. Let's go to our cell B2, and then let's do import Icepak project, hit browse. Let's go to our documents. Let's, you know, go to where our main folder is. So we keep digging down, DP0, pick Icepak, and then we see the folder here. And let's hit OK. So now this is going to import and open up a new Icepak model, which you can see is just the submodel that has the two blocks 4, 5 and the plates 1 point. So now let's define our plate 2.2 with more detail. Let's name it chip. And let's make sure the geometry is right. Let's switch to start length. This should be and that should be 5. Let's go to properties and then change the total power to 3 watts. Let's hit update and done. So what has happened is, we now have instead of one big chip, we're going to resolve individual chips. So we resized it to a single one. Now what would like to do is replicate this on the board. Let's do a right click, and I want to copy this object, and I want to essentially make one copy with a Z offset of 0.065 meters. I'm gonna let's make 2 copies, I'm sorry, and hit apply. So now we kind of have our top row pattern done. So what we'd like to now do is make copies of these 3. Let's go ahead, replicate our chip. So we want to do a copy. We want to make 2 copies, and in the Z direction with a minus 6.5 centimeters. So let's hit apply. Now we have 2 new chips. Next step is going to be replicating these chips in the Y direction. So let's mark all 3. Copy. Let's make 3 copies of them. We want to translate them with a Y offset of 7 centimeters. Let's hit apply. So now we have filled in the matrix for the chips. Let's switch to an isometric view, and what we would like to do is remove 2 chips from the system. So I'm going to remove chip 5.3, and then let's see. Chips, and I want to remove chip 8. Now that our geometry is completed, we want to generate our mesh. So let's click our mesh generation button, and here let's define our maximum element size. We want to be fine in the X direction. Let's set it to 3 millimeters, and let's set Y and Z directions to 20 millimeters each side. We can have the same minimum gap, and let's change this mesh parameters to coarse. Also, let's go to local. We don't want to do object parameters, and we're ready to generate our mesh. Let's hit the generate button, and it came back with certain number of elements, around 10,000. We can display it, and all right, so does a little refinement around our chips, and the quality looks again very good. So we can close this. Before we go to our run, let's go ahead, pick kind of randomly a chip and drop it under point so we can track, and then let's pick another one, also drop it. Let's drop it under points. All right, Let's go to solution settings, basic settings. Open it and make sure we have 300 iterations. Hit accept. Then we can essentially go under solve and run solution, or just click the calculator button. So now the job is sent to Fluent and we're going to wait for convergence. So again, we have our solution here, the similar strategy for solving for flow, and then just doing a couple of iterations for temperature, and looks like we have a converged solution, so we can hit done. And then next step is going to be post-processing the results for the subdomain. So let's do a face object, and what we'd like to do is obvious to look at the temperatures on all of the chips. So let's select all the chips using button, hit accept. Let's look at contours of temperature. Let's do this object. And let's see, let's switch to smooth shading and then hit apply. So now what we do see is, the temperatures on each of these chips, because we removed 2 chips for this region, so that there's a bit more air going through this region, cooling down these, and then these 3 chips are not getting enough airflow, and they seem to be the hottest ones. Let's add some particles. Let's pick our release from our inlet. So min y is our inlet. So let's hit accept. What we want to see is particle traces. Click on it. Let's color it by temperature. Then let's set this to 100. Maybe put dots, and let's hit apply. Let's see how it looks like. So this is now showing us the flow distribution. Maybe remove the dots. Ooh, trail marker. See size, maybe make the dots smaller so that we can see how the flow is going, what the temperatures are. We can also look at the speed. It applies, so now it's colored by speed. So, this essentially completes the the zoom in demonstration. So again, what we've learned is, if we wanted to do this detailed simulation in the full system, we would have needed to make all these resolution for all of the 10 different PCBs. But what we did was, first in the bigger model we solved for the whole domain, and then what we did was we did cut a small section out of it as a submodel, where the flow information at the boundaries are coming from the main model, and then we have different geometry inside the submodel, which is finally resolved. And now we can look at quick turnaround studies of maybe placement of chips, etc. So we can do a much faster turnaround and resolve the details within the zoom in domain. So thank you for your interest. This concludes our presentation. Have a good day.